Okay, we're going to start here over sample surveys. This is chapter 12 in our book. We have learned ways to display, describe, and summarize data up to now, though our conclusions have been limited to a particular batch of the data we are examining. That's okay as far as it goes, but it doesn't go very far. We usually aren't satisfied with conclusions based only on this group of customers, or the people who are answered the survey on this particular day. To make businesses decisions, to do science, to choose wise investments, or to understand what voters think they'll do in the next election, we need to stretch beyond the data at hand to the world at large. To make that stretch, we need three ideas. You'll find the first one natural, the second one may be more surprising, the third one is the strange, but true facts that often confuse those who don't know statistics. Alright, so let's talk about those three big ideas first. The first big idea is to examine a part of the whole. That's what samples are all about. So remember, the whole is the population. So the population is everybody we're interested in. Okay? And what we do is we examine part of that whole, so we take a sample of that population. Okay? So this population size could be very, very big. Who knows? It could be small as well. Maybe the population is only sophomores at Twinsburg High School, and it'd be fairly small. But for the most part, populations are usually pretty big. So we take a sample of size n from that population. Now, the two things that we look at with populations and samples, for example, first off for samples, and we have populations as well, one thing that we look at is the average of something, whether it be the average height or the average waist size or the average amount of something. We look at a sample and we look at that average. Now in a sample, the average we've heard is x bar, in the population it's mu. That's nothing new to us. We've talked about that before. Samples have statistics, populations have parameters. But another thing that we also look at that we haven't necessarily, we've talked about but maybe not necessarily hit on exactly, is that we look at proportions a lot. You know, what percentage of people are going to vote for candidate X in the next election, or what proportion of people don't wear their seatbelts, or so forth. So we talk about proportions a lot as well. In a sample, we call that proportion p hat. So P for proportion. The hat is indicated it comes from a sample, where in a population we say true P. So just P without a hat. So again, if I said that, we're interested in the percentage of people that wear seatbelts, maybe the true population proportion that we'll never really know, but maybe the truth is 73%, and our samples showed 79%. That would be p hat. So these are the two important things we look at when we talk about examining the part of the whole. As we talk about averages or means, and we talk about proportions. And samples must represent that population. If the sample is a well-selected one, it can accurately represent an entire population. But again, it's got to be a well-selected one. Idea number 2 is really important as well. And idea number 2 is to randomize. All samples must be selected at random. Randomizing protects us from the influences of all features of a population, even ones we might not have thought of. So if we think about, there could be a difference between male and females, well, what we do is we select a sample randomly, and the randomness should give us some females and some males, as long as we at least thought about it. But it also, the important thing about randomizing is that even if there was another characteristics that we didn't think of, for some reason like eye color, maybe eye color had something to do with our survey, and we didn't even think of it, well then a true random sample should give us blue-eyed, green-eyed, brown-eyed. It should give us a total mix of the different eye colors out there. So again, randomization really protects us from features of populations that we didn't necessarily thought of. It makes it very nice and split evenly. Randomness allows for it to just, be random. It also allows us to make inferences. Now remember, think inferences are statistical predictions, smart statistical predictions about the population. So if a sample is truly random, then we can make these smart statistical predictions, called inferences, about the population from our sample. So randomness is necessary in every type of sample. The third idea is kind of an interesting one. And the third idea is that the fraction of the population that you've sampled doesn't matter. It's the sample size itself that's important. And sometimes it's hard for kids to quite understand this, so I'll explain as best I can. Some people think, oh, you need to sample at least 15% of the population for it to be a good sample. It's not true at all. It has nothing to do with the fraction, percentage, or proportion of the population. It's all about your sample size. Obviously, a small sample won't yield accurate results. So obviously, a sample of 5 people is probably never really going to be a good sample. But most think that you need a large percentage of the population, and that's simply not true. What's important is the size of the sample. It has nothing to do with the size of the population. Your population could be millions or thousands, and the size doesn't matter. It's about the size of the sample, not the size of the population. Let's continue to talk about this. Usually a good sample size of 1,000 will always be a good enough sample regardless of population size. It's the random selection process that produces a random sample that allows us to be confident that the sample represents the population, even when the sample consists of only a small fraction of the population. So the idea is, if we had 5,000, or let's make it like 10,000 people in our population, or a million, I mean that's a big difference, 10,000 versus a million, a sample of size 1,000 will probably be good enough for either one. Even the size of a million, as long as you choose those 1,000 people truly randomly, you're going to get a good sample. Now obviously, if your sample is only 1,000 people at Twinsburg High School, well, then, you probably don't need 1,000 people, obviously, okay? That would be called a census then if you ask everybody. The idea is that you'd probably maybe only need 50. Really, 50 could probably do it. So again, think about a sample size is more important about the size of the sample than it is trying to relate it to the population. That's an important topic we'll talk a lot about in class. Okay? Now that we've talked about the 3 big ideas, let's talk a little bit more about creating these samples. Well, first off, before we actually talk about how to make a sample, we have to make sure that we understand that good samples avoid bias. Bias is any systematic failure of a sampling method that allows the sample to not accurately represent the population. So anything that can take place in you getting a sample that could cause the information from that sample to be biased or not represent the population would be considered biased. Bias in a sample can come, sorry for the typo there, bias in a sample can come from how the sample is drawn from the population, or it can come from the way in which this information is obtained once the sample is selected. So there's 2 ways you could have bias. You could get bias from how it was selected, or you can get it from how you got the information once the sample was selected. And I'll clarify those 2 differences as we look at some specific examples of bias now. Okay, these are very, very common forms of bias. And the forms of bias we're going to talk about right here, these 3, are called selection bias, or they're based on how the sample was selected. So the first bias is known as selection bias, and this means how you selected sample was poor. So something that you did in selecting that sample was poor, that made it not accurately represent the population. Okay? So maybe if one type of selection bias is something we call convenience bias, and this is just saying, well, you know what, I need to choose 20 students from Twinsburg High School. My population is Twinsburg students, and I need to choose 25. You know what, so I'm just going to use the 25 kids in my Block 1 class because it's easy for me. It's convenient for me to just sample them. Well, my sampling selection idea there was biased. That's going to be very biased because I'm just choosing a sample that's convenient for me. That's not a truly random sample. That's an example of selection bias. Or just asking your friends. That's another example of selection bias. Why? It's convenient to ask your friends. Well, how you selected that sample is biased, and it doesn't represent the population. Okay? Another form of selection bias is volunteer bias. Asking for volunteers is always very bad, because what happens when you ask for volunteers is that you get people that are either really, really strongly for or people that are really, really strongly against something. You never really get to know the people in the middle that tend to be the most important sometimes. So anytime you ask a sample and you collect your sample just by simply asking volunteers, it's very, very poor sample. It's not going to be random. It's not going to represent the population. The third type is non-response bias. Non-response bias is when you choose people to be in your sample, but they do not respond. They don't answer your questions. So a good example of this would be mailing surveys. So you select 1,000 people and you mail a survey to them, and in the survey you ask that they return it to you. But hey, what do you know? At the end of the day, 100 people never even return the survey to you. That's an example of non-response bias. You cannot allow those people to not give their opinion. If they were chosen to be in the sample, you need to get responses from them. Okay? So the idea that why non-response bias is so important, it's the difference. I spelled that wrong. It's the difference between those that do respond and those that don't. That becomes important. I spelled that wrong too. Becomes important. And what I mean by, a lot of times some people might say, well, oh, who cares? Those 100 people didn't respond, just don't use them. Well, it's the difference between their opinions and the ones that you did get that is really important. And you need to understand that difference. So if you never get those responses, you're never going to know. So a lot of times kids say, well, what do I do when 100 kids don't respond? Well, you call them. So maybe they didn't send their letters back, so you call them. Okay, so maybe you get 50 more that answer your survey because you call them. But what about the other 50? Okay, you call them again. You send them emails. And if all else fails, you go to their houses. You wait until they get home. The point is, if you choose 1,000 people to be in your sample, you need to get 1,000 responses. So if people do not respond, it's important that you get their response. So you have to come up with an alternative method to get their response. So those are the three forms of bias that happen because something you did in your selection process caused the sample to not accurately represent the population. Okay, now here's the other two types of bias. Now, these biases are formed, maybe you do have a good sample. Maybe you do call 100 people and you get everybody to participate. No volunteers, truly random sample. Okay, these forms of bias come from how you get the information from the people. So response bias has nothing excuse me. Response bias has nothing to do with the responses. It's the fact that how you ask the question, how you word the question, causes the response you get to be biased. So think about response bias. It has nothing to do with the opposite of non-response bias. Response bias means the response that you get is biased. Now, why could that be? Well, a classic example of response bias is if a dentist wants to know what percentage of people floss every day. So the dentist asks you at your monthly or your semi-yearly or whatever, your biannual checkup, dentist says, do you floss? Well, of course, if the dentist asks you, you're going to say yes. Every time the dentist asks me if I floss, of course I say yes. But the reason why I said yes, which was a lie, was because it was the dentist asks me. I didn't want him to feel bad, right? Another example could be if in class I want to get an example. I wanted to get a sample of students, and I wanted to find out what percentage of kids at Twinsburg High School smoked marijuana. So I get my sample. It was a great sample. All 50 kids that I got come to my classroom, and then I asked them, all right, raise your hand if you smoke marijuana. Well, a lot of kids are going to be afraid to admit to their teacher, or they don't want to admit to an adult even, not necessarily even their teacher, that they smoke marijuana. Or they don't want their friends in the classroom to know that they smoke marijuana. So what they do is they lie. They just say, oh no, I don't smoke marijuana. So that's a form of response bias. So again, it was either, maybe it has something to do with the question being worded funny or who's asking it. Another form of response bias could be how it's worded. So response has to be who is asking question. Who is asking question. Another way that we can have response bias is the wording of the question. So for example, if I'm asking a survey about pollution and I say, oh, the city of Twinsburg is really polluted. There's dirt and there's trash and there's litter all over the place. What do you think about the pollution in Twinsburg? Well, people might say, wow, yeah, they're right. There is a lot of trash. There's a lot of litter in Twinsburg. So, yeah, you're right. It is a lot of pollution in Twinsburg. So the idea is you don't want to have any kind of leading words or anything that could influence your response. You just want a straightforward question. Is there pollution in Twinsburg? What are your thoughts on the pollution of Twinsburg? You don't want to have any leading questions that can give somebody a chance to maybe change their response based on the wording. So once again, a response bias is anything that you could do to the person that's going to make them change their true response to you. Okay? One other thing that we call here is we call it social desirability. And what I mean by this is desirability. I'm not sure if I'm spelling that right. But most people want to look socially good. They want to be socially acceptable. So if you ask them a question about something that's not necessarily socially acceptable, and you ask them that in front of their peers, they might lie because they don't want people to know. So it's kind of the same thing with the marijuana, is you might lie, not because who's asking, but you might lie because you don't want your friend next to you knowing. Okay? Measurement bias basically deals with how you measure the response is biased. A very simple example of measurement bias is that maybe you want to get the weights of people. So you have a sample and you want to get an average weight. So the people step on your scale, but your scale was broken. So you were getting inaccurate results because your scale was broken. So measurement bias would be something is wrong with your measuring of that particular variable. Okay, that's measurement bias. Now, let's talk about, now we talked about bias, let's talk about the sampling methods that are out there. There are several sampling methods. Now, before I start with this one right here, I want to talk about a census. Okay, so just want to write that down in your notes, a census. A census is a sample where you get everybody in the population. Every single person in the population is in your sample. Sounds like a great idea, but most of the time it's very hard to do. It's expensive and very, very time consuming. A census is only good if you have a very small population. So maybe I'm a small business owner and I have 100 employees and I want to get the feelings on changing a coffee maker. You know, I want to get a different coffee maker in the workroom and I want to know people's opinions. Well, 100 people, that wouldn't be so hard to send out an email asking people's opinions. So in that sense, a census would be okay. Or maybe my population was the AP statistics students in Twinsburg High School. There's 74 of you. So if I wanted to get information, or maybe I wanted to get some thoughts from you guys, asking everybody wouldn't be that hard to do. So a census is possible, but not always the best, especially when your population is really big. Okay, so here's the main different type of sampling methods. The first one is called a simple random sample. In a simple random sample, we usually call a simple random sample an SRS. So if you ever see that, it stands for simple random sample. Simple random sample is every possible sample of n subjects has chance to be selected. Now, one thing that a lot of kids get confused with here is they think that a simple random sample means every person has a chance to be selected. Well, you're going to notice that in every single thing that we talk about, every method we talk about, every person has a chance to be selected. So a simple random sample is not about every person having a chance to be selected. It's about every possible sample of size n subjects has a chance to be selected. So if we look at this grid down here, imagine that this is, I think, like 12 by 14. So imagine that every little spot here represents a person. And I want to randomly choose 10 of them. So what I could do is I could give everybody a number, 1 through whatever I got here, okay? And what I would do is I would then give everybody a number, and I would either use a random number table to randomly select 10 numbers. Now, if I pick a number that's not on here, I would have to say I'm going to ignore it. And if I pick a number twice, I would have to ignore repeats because I can't have the same person be picked twice. So again, everybody would get a number. I could use a random number table or I could use my calculator. Please don't ever use the, oh, pull a number out of a hat method. Don't ever say that. It's either a random number table, or a calculator. Okay, and I would prefer that you actually stick with a random number table, but a calculated method can be used when we use the random integer feature on our calculator, and we would allow the calculator to randomly pick numbers for us. Okay, and again, you have to make sure you ignore repeats and you ignore numbers that aren't there. Okay, so if this is like 1 through 150, for example. If 160 comes up, I'm not going to choose 160, obviously. Okay? And if there are over 100, then you need to use triple digit numbers. So you'd use 0, 0, 0 through, say, 150, if that's how many I had. Okay? I don't forget how many are there. So that way, like, you would need 0, 0, 1. You'd have to look at 3 digits at a time since you have that many options. Okay? So that's a simple random sample. Okay? And I'm going to come back to that shortly here. Okay, in a stratified random sample, what we do in a stratified random sample is we separate into groups, and we separate what we call into homogeneous groups. Okay, that means we separate them into groups that they have something in common. Okay, so all the groups have something in common. So we're going to separate them into groups of people that have something in common. Something as simple as males in this group, females in that group. Or maybe we can do race. We could do white in this group, Asian in this group, African American in this group, Hispanic in this group. Okay, or we could do grades, sophomores, freshmen, seniors, juniors. You separate into groups, and those groups are homogeneous. Homo means the same. So people within those groups are the same. Okay, so I'm going to write that down. Within groups, the same. Okay, so the groups themselves would be different. So the female versus male group, those groups would be different, but within the group they're the same. So it's important that we understand that. Then we randomly select a set number from each group. Okay? So we separate into homogeneous groups. Within each group, they're the same, and then we randomly select a set number from each group. So let's say that we break our group. So we got all of our people. We're going to break this group into Asians, African Americans. These are the whites. Then we got Hispanics, and then we got other, whatever. I know I'm skipping some, but I'm just trying to give you a general idea. So we break into these homogeneous groups, and then I'm going to say, okay, I'm going to select 5 from this group, 5 from this group, 5 from this group, 5 from this group, and 5 from this group. How am I going to do that? Randomly. That's important to have that randomness, right? So everybody in this group gets a number 1 through however many are in there. Maybe there's 20 in there. So everybody gets a number 1 through 20. I'm going to randomly use a calculator or a random number table to select 5. Then I'm going to go to this group and do the same thing. Okay. Another example of this could be like maybe we have maybe we're a toy manufacturer, right? We got a bunch of crates of toys here. So we got all these crates, right? Okay. So let me break this up into a 5 right here as well. Okay, I don't mean for those to be overlapping. So I got all these crates here. I got a bunch of crates here, a bunch of crates. All these crates have the same toys in them. So I'm going to break them into groups. Maybe the boxes. Here's a box of toys, So I got 6 boxes of toys, and I'm going to take 5 from each. So the key thing there is that we take a couple from each. That's stratified. So think stratified. Break into groups. Take a couple from each. How do I take those couple? Randomly. Now, a lot of times kids say, well, what's the difference between stratified and simple random? In both, everybody had a chance to be selected. Trust me, everybody had a chance to be selected. But think about the group where I have boys and girls, right? If I take 10 boys and 10 girls, that means a group of all girls never had a chance to be selected. And remember, in a simple random, every possible sample of size n had a chance to be selected. So that chance of all girls never had a chance to be selected. That's why that is stratified, not simple random. Or think about my stratified case where I took 5 African Americans, 5 white, 5 Asian, 5 Hispanic, right? Well, a group of all African Americans, all 20 or whatever African Americans, that group never had a chance to be selected. See, in a simple random sample, it would be possible to end up with all African Americans. In a stratified, that would never be possible because of the way you took a couple from each. Okay, the next is cluster. And this is another one we have to make sure we explain real well here. In a cluster sample, we break or separate into heterogeneous groups. I think I spelled that right. Maybe not, but oh well, you get the point. Heterogeneous groups. Now, hetero means different, right? So in heterogeneous groups, we have different people in every group. So we separate into groups, and in each group we have a mix of males, females. We have a mix of races. We got African American, we got Hispanic, we got Asian, we got white. We got all these. So each group is different, right? So within groups, very different. Within groups, very different. Right? So what happens is when we break into clusters, all the clusters are similar. So within each cluster, they're very different, but every cluster is built like that. So the clusters themselves are all very similar, but within they're very different. Seen stratified, inside each strata, there is something very similar. And then all the stratas are different from each other. That makes sense. So the idea here is, let's say that we have our population here, all these boxes, right? So we're going to separate into clusters, right? So now this cluster right here is a mix of all different kinds of people. So is this one, so is this one, so is this one, so is this one, so is this one. So each cluster is a mix of different kinds of people, right? And then what I do is I randomly go in and select 5. Or I'm sorry, okay, all right, take that back. Hold on a second. So I create groups that they all are very different. And then what I do is I randomly select one of those clusters to be my sample. So I don't take a couple from each, I take one cluster. How do I choose it? Randomly, of course. So I label this one 1, this one 2, 3, 4, 5, 6. Use a random number generator to pick a number 1 through 6, and the first number that comes up becomes my sample. So I break into clusters, and then one of those clusters becomes my sample. Now, you could also have a case where you have a whole bunch of clusters. Maybe you have 20 clusters and you choose 3 of them to be your sample. That can be fine too. The key difference between cluster and stratified, in strata groups, you break into groups and take a couple from each. Cluster, you break into groups and just take 1 or maybe 2 clusters to be your sample. So hopefully that makes sense. The last one is probably the easiest to understand, a systematic sample. A systematic sample just means that you have some type of method to how you sample. So usually you're going to take the kth person to be in sample. So what's going to happen here is maybe we need a sample of Twinsburg High School students. So we go to the front door and we wait for students to come in, and we select every 5th student. So I'm going to come in here, I'm going to take 1, 2, 3, 4, 5. This guy becomes my sample. 1, 2, 3, 4, 5. This guy's in my sample. So every 5th student that comes in the door is in my sample. Or I could get an alphabetical list of all the students in Twinsburg High School, and I select every 5th kid. But realistically, that list should be a complete mix. That list should be all mixed up, and then I take every 5th off that list. Okay? There could be some bias in this, and if I stand at the door outside Twinsburg High School and I select every 5th kid that comes in the door to be in my sample, the issue with that is what if somebody's absent that day? Then they never walked through the door, hence never had a chance. Now that could be some form of selection bias. Remember, selection bias is when something about my sampling technique creates the sample to not represent the population. So all of a sudden, kids that are absent never had a chance to be selected. That's not really fair. So you've got to be careful with systematic. It is a very acceptable sampling method as long as you're very careful on the lists you're using or the people coming in do accurately represent the population. Okay? All right, a couple more quick additional topics I want to talk about real quick here. Dealing with what we've been talking about. And one is multi-stage. Some sampling methods would involve multi-stage, meaning that you do this, you break them down into these stratas, and then you take a couple from each, and then from those stratas, you're going to now do a simple random sample. So multi-stage would be you maybe do a couple different things together to create your sample. A little bit rare. We'll look at some special cases of that. We did mention convenience samples. Anytime you pick a sample by pure convenience, just selecting the first 5 kids that you see come in through the door. That's very, very poor, not going to represent the population. Volunteer samples also, again, I mentioned that earlier, anytime you create a sample based on volunteers, it's a very, very bad sample. Okay? And the last thing I want to do is, sorry, it kind of got cut off here. I apologize. It says so important, so pay attention. So sampling error, okay? Sampling error is something that we're going to talk a lot. We're going to talk a lot about it in the next couple weeks. Sampling error is not bad. Sampling error is not an error. Okay, I want to make sure I'm very clear on that. What sampling error is? Sampling error is the idea that if I take a sample of students from Twinsburg High School, and Sean takes a sample, and Preetham takes a sample, and Kaylee takes a sample, and Sammy takes a sample, and Mackenzie takes a sample. We're all going to create different samples, okay? And my sample might get a little bit different result than Sean's, or than Preetham's, or than Mackenzie's, or than Sammy's, or than Kaylee's. So sampling error is the natural variation between samples. Natural variation between samples. So let's go all the way back to what I mentioned in the beginning. What percentage of people don't, or what percentage of people do wear their seatbelts? Well, maybe I get a sample, and my sample shows that 72% wear their seatbelts. Maybe Preetham gets a sample, and his shows that 75% wear their seatbelt. Maybe Sean gets a sample, and shows that 63% wear their seatbelt. Maybe Sammy gets a sample, and it shows that 98% wear their seatbelt. Okay, well, we're all going to get different results because they came from different samples. That's called sampling error. It's not bad. It's not an error. It's just the natural variation that's going to occur between different samples. Okay, so I should have an S on there for between different samples. All right, so hopefully that is very simple. So don't overlook sampling error. All right, that's it, guys. I know the video is a little bit long, but make sure you take good notes, and we'll do a lot of problems in class dealing with how to create and how to build very good samples.